You ever get that feeling? When something that seemed all tangled up just clicks into place, like a satisfying aha moment.
Oh, absolutely.
Well, get ready for a whole bunch of those, because today we're diving into a really thought-provoking area of quantum physics. But don't worry, no equations here.
Right.
It's more about how we think about what those equations mean.
Yeah.
Specifically, we're looking at quantum Bayesianism, or Qism as it's often called, and a whole family of related pragmatist views.
Very interesting stuff.
Yeah, and you, our listeners, pointed us to some seriously rich material in the Stanford Encyclopedia of Philosophy.
Excellent resource.
So our mission, if you will, is to really unpack those key insights, especially how these perspectives challenge the idea that quantum theory is giving us a direct picture of reality itself.
It's definitely a different way of looking at things.
Ready for some mind-bending aha moments?
Oh, man.
Okay, so let's kick things off with Qism. Even the name itself is kind of suggestive, right? It evolved from quantum Bayesianism, which already hints at the blending of ideas here.
Exactly.
And it's really closely associated with the work of Caves, Fuchs, and Shack.
They've done some fascinating work in this area.
Yeah, they have these really accessible introductions if you're interested in digging deeper, plus a popular book by von Baer that's worth checking out.
Oh, yeah, that's a good one.
So for someone approaching this from, say, a philosophy background, what's the big shift in thinking that QBism brings to the table?
Well, the core idea is that a quantum state, the kind we deal with in quantum mechanics, it's not actually a description of some physical system out there in the world.
Interesting.
Instead, QBism says it represents an agent's, like you or me, their epistemic state. So basically, it's all about degrees of belief, subjective probabilities about what'll happen if you interact with the world in a certain way.
So it's not about the system itself, but about our knowledge of it.
Precisely. It's moving away from what the system is and towards what we know about it. So the key takeaway is that QBism isn't telling us about objective reality. It's a guide for how you, as an observer, should rationally update your beliefs based on what you experience.
So it's not a theory of the world. It's a theory of how we understand the world.
That's a great way to put it.
That's a pretty big change in perspective.
Yeah.
So how does this idea of the quantum state being about knowledge then impact our understanding of quantum measurement? That whole thing about how a quantum system goes from being in a superposition to having a definite outcome.
Ah, yes, the measurement problem. That's where things get really fascinating. You see, QBists don't see the outcome of a quantum measurement as revealing some pre-existing objective property that was hidden.
It's not like uncovering a secret code or something.
Not quite. For them, it's a personal experience of the agent who's doing the measuring. It's about your interaction with the world leading to a unique experience for you. And that experience then updates your beliefs about the system.
So it's not about finding out what's already there. It's about having a new experience that changes what you know.
Exactly. It's less about uncovering a hidden reality and more about how your interaction with the world shapes what you know. And for a philosopher, this reframes measurement as an act of gaining information and updating your personal subjective probabilities.
Which brings us, of course, to probability itself. It's so fundamental to quantum theory. So how do QBists, with their emphasis on the agent, how do they interpret those probabilities that we calculate?
Well, true to their agent-centered view, they go with a subjective Bayesian interpretation of probability.
Subjective Bayesian.
Right, sometimes called personalist. This is drawing on ideas from people like D. Finetti. They see probability as a measure of an individual agent's degree of belief.
So not objective chances out there in the world, but beliefs held by a person.
Exactly. So the Born rule, the one that gives us the probabilities of different measurement outcomes, it's not seen as some objective law of nature. Instead, it's more like a guide for rational thinking, an empirically motivated norm of rationality.
So like a rule for being consistent in your beliefs.
That's the idea. A rule to make sure your web of beliefs about the world is coherent and doesn't contradict itself, especially when dealing with uncertainty.
That makes sense. Now, the Born rule is usually formulated using quantum states. But you mentioned that QBists have their own reformulation of it. Can you tell us about that? What's the thinking behind it?
Yeah, so QBists prefer a formulation that directly connects probabilities to each other, without explicitly needing an objective quantum state.
Okay.
Their version is often expressed through what they call equation 2.
Equation 2?
It involves the probabilities of actual measurements and then these hypothetical fiducial measurements.
Fiducial measurements. That sounds complicated.
They are a bit technical, but think of them as a kind of standard measuring stick that helps them connect all possible measurement outcomes in a consistent way. These fiducial measurements are also called SICs. Yeah, that stands for symmetric, informationally complete, positive, operator-valued measures.
Wow, a mouthful. So what's the point of this equation, too?
Well, the idea is that this equation is a fundamental condition for what they call quantum Bayesian coherence. It makes sure your subjective probabilities for different possible experiences are rationally linked, they fit together properly. And there's actually an ongoing debate about whether these SICs actually exist in all the relevant mathematical spaces.
So it gets pretty deep into the theoretical weeds.
It does, but it shows how foundational this element is for the whole QBist framework.
Now, this subjective view of probability, it seems to clash with how we usually think about probability 1, right? Like when we say something has probability of 1, we usually mean it's certain to happen, like it's a fact about the world.
Right.
So how do QBists deal with this, especially when you have thought experiments like the EPR paradox, which rely heavily on these probability 1 predictions?
That's a great point, and it gets right to the philosophical heart of QBism. Remember, the EPR paper argued that if you can predict the value of something with absolute certainty, meaning probability 1, without actually messing with the system, then there has to be a corresponding element of reality, something physically real.
Right.
But QBists, they challenge that whole line of reasoning. They say probability 1 just means that an agent is completely certain about the outcome based on their current knowledge.
It's a belief, not necessarily a fact about the world.
Right. And another agent, someone with different experiences or different information, might not have that same level of certainty.
Makes sense.
So for QBists, the EPR argument for quantum mechanics being incomplete, it falls apart because they reject this idea that probability 1 automatically means something is physically real. Certainty is always relative to an agent's individual knowledge.
That's a really interesting way to think about it. Now, the whole measurement problem, the apparent collapse of the wave function from this blurry superposition to a definite outcome, it's been a huge headache in quantum mechanics. How does QBism, with its focus on knowledge, how does it deal with this problem?
Well, because QBism doesn't see the quantum state as some complete and objective description of the physical world, there's no real physical collapse happening.
No sudden dramatic change.
Nope. It's simply the agent updating their beliefs based on the new information they got from the measurement. Think of it like this. Different agents with their own unique experiences and information, they might legitimately assign different quantum states to the same physical system.
So different perspectives, different states.
Exactly, and that's totally fine in QBism. Now, as they share experiences and communicate, their beliefs might start to converge. But there's no rule that says their quantum state assignments have to become identical. So the measurement problem kind of dissolves because the quantum state itself isn't something physical that's undergoing a dramatic collapse.
It's more about how our knowledge changes.
Okay, that makes sense. And what about non-locality? That spooky action at a distance that Einstein was so famously skeptical of? How does QBism handle the correlations we see between entangled particles that are far apart?
QBists avoid the whole non-locality issue by focusing on the individual agent's experiences, which are always local, both in space and time.
Local meaning happening in a specific place and time.
Exactly. So when Alice, let's say, measures a particle and gets a certain outcome, and Bob, who's miles away, measures his entangled particle and gets a correlated outcome, those are both local experiences for Alice and Bob.
They're not instantly influencing each other across vast distances.
Not from a QBist perspective.
Okay.
When Alice learns about Bob's outcome, maybe through a phone call or something, that's a new experience for her, but it's still happening right where she is. So quantum theory, for QBists, is about the relationships between those individual local experiences, not about spooky actions happening across space. So the correlations are in the knowledge, not in some weird faster-than-light communication. That's a neat way to look at it. What about decoherence? That's often presented as the explanation for how the classical world, the one we experience every day, emerges from the quantum realm. How do QBists interpret decoherence?
Well, remember, they don't see the Schrödinger equation as some law that governs how an objective physical state changes over time.
Right.
So decoherence, which relies on that equation, can't be seen as some physical process that makes quantum systems behave classically. Instead, Fuchs and Scheck, they see decoherence as a kind of consistency check on the agent's beliefs about future
A
measurements.
consistency check.
Yeah, it's about making sure your probabilistic expectations at a single point in time are all hanging together properly, especially when you're thinking about a whole series of potential measurements. It's more about the rational structure of your beliefs than about some physical process acting on the system.
QBism seems very focused on the individual. Are there any broader frameworks or ways to generalize these ideas?
Yes. One interesting extension is what Merman calls QBism, or classical Bohrism.
QBism.
Right, and it takes this focus on immediate experience to an even deeper level, like even our perception of now, the present moment. He argues that the present moment is something fundamental, something physics should ultimately account for. And he sees space-time as this abstract framework that we use to organize our experiences.
So it shares that emphasis on experience being central. Now, I can imagine philosophers raising some objections to QBism. One of the common ones is that it seems awfully close to solipsism. You know, the idea that only one's own mind is real and everything else is uncertain.
Yeah, that's an understandable concern. But Merman addresses this head on. He says, look, his experience of interacting with others, like you and me, leads him to believe very strongly that other people have their own experiences just like he does.
So it's not denying the existence of other minds?
No, not at all. He says he couldn't function in the world without that belief.
It makes sense.
And he points out that science is all about collaboration, people sharing their experiences and trying to build models that explain them. Communication is key.
Makes sense. Another criticism you often hear is that QBism is just instrumentalism dressed up in fancy language. You know, the view that scientific theories are just tools for prediction, not attempts to describe reality.
That's another one that comes up a lot. And it's true that QBism, with all this talk about quantum theory being a user's manual, it can sound a bit instrumentalist. But Fuchs, he prefers the term participatory realism.
Participatory realism.
The point is that while quantum theory might not be describing some objective world that exists independently of us, it still plays a crucial role in how we engage with reality. It's just that the role is indirect.
We participate in shaping reality through our actions and choices.
Right. And he argues that the Born rule itself, in its most general form, hints at something real, some structure in the world that constrains our experiences. Merman, while agreeing with much of this, might lean more towards the idea that science is a personal tool we each use to organize our own experiences, and that the world of science we talk about is something we jointly construct through communication and shared practices.
It seems like QBism emphasizes how we use our knowledge to interact with the world.
Absolutely. It's very much about action and experience.
Now, philosophers of science often argue that good scientific theories should explain things, not just predict them. Like, why do certain materials conduct electricity? Can QBism offer those kinds of explanations?
That's a major point of debate, for sure. Critics like Timson argue that QBism struggles to give us real physical explanations.
Because it can't point to objective quantum states and processes.
Right. Explaining things in QBism seems to boil down to just updating an agent's beliefs, not really getting at why things are the way they are in the world. But cubists, like Fuchs and Scheck, they might counter that even in realist interpretations of quantum mechanics, the explanations we get are often probabilistic. They're not giving us deterministic cause and effect stories.
It's more about chances and possibilities.
Exactly. So they might say that ultimately scientific explanation is about building a coherent framework for an agent's beliefs and expectations, and that QBism does that quite well. Plus, they'd point out the conceptual problems that realist interpretations run into, problems that QBism avoids.
So it's a different way of thinking about what an explanation is.
It really is.
Now, Bacci-Galubi, he has a specific objection about the cubist version of the Born rule. He questions whether it really holds up as a new Bayesian norm. What's his argument there?
His point is that the usual way we derive the Born rule, it relies on assumptions about the physical symmetries of quantum states and how measurement devices work. QBism, on the other hand, takes its reformulated Born rule, that equation 2 with the SIs we talked about, as fundamental.
Right.
So Bacci-Galupi is asking, can QBism really justify this crucial assumption that the probability of an outcome doesn't depend on how you do the measurement? Can they ground that procedure independence solely in their framework of subjective probabilities? And the whole question of whether SICs exist in all the necessary mathematical spaces adds another layer of complexity.
It's a deep and challenging question for QBism to address.
It definitely is.
Okay, let's talk about the elephant in the room, or maybe the agent in the room. Subjectivity is obviously a central part of QBism, and it's a big target for those who favor more objective interpretations of quantum mechanics. Isn't QBism just too reliant on individual beliefs, which can be pretty different from person to person?
That's the core of the disagreement, for sure. A lot of physicists and philosophers hold that quantum states are objective, that they're real features of the world. Cubists flatly deny that. And that leads to some fundamental differences in how they view things like quantum dynamics and the meaning of measurement outcomes.
It's a clash of perspectives.
For sure. And when cubists say measurement outcomes are personal experiences of the agent, that really challenges the idea of objective scientific observation, which is so central to how we usually think about science.
Can science be truly objective if it's all about subjective experiences?
That's the question. And critics worry that this subjectivity undermines the authority of scientific reports and the arguments for why different people should eventually converge on the same beliefs, even if they start with different experiences. Even the cubist interpretation of probability 1 as subjective certainty clashes with the EPR argument, which ties it to something objectively real in the world. And some argue that even folks who prefer objective interpretations could borrow some of cubism's strategies for dealing with non-locality without having to go all in on the subjectivism about probability and quantum states.
It's a lot to unpack.
It really is. It gets right to the heart of what we think science is all about.
Now, Myhrvold has this interesting argument about prepared quantum states. He basically says if you're taking quantum mechanics seriously as a guide for what to believe about the future, then you should believe that preparing a system in different quantum states really corresponds to different physical states of affairs in the world. But cubists, they don't buy this. Why not?
Well, cubists, like Fuchs and Schack, they really embrace quantum indeterminism. They say nature does what it wants, meaning that the outcomes of quantum measurements are fundamentally unpredictable. There are no hidden variables or deterministic mechanisms controlling things behind the scenes.
No predetermined plan.
Nope, not in their view. So for them, preparing a system in a particular quantum state doesn't mean you force the system into some specific objective state. It's just a way for the agent to update their beliefs about what might happen when they interact with the system in the future.
It's about managing expectations, not controlling reality.
Exactly.
I know there are some other objections to cubism floating around out there.
Oh, definitely.
Could you give us a quick rundown?
Yeah, so Brown, for example, he's argued that cubism has shades of Berkeleyan idealism to it.
Berkeleyan idealism. That's a pretty hefty philosophical label.
It is, and he's not a fan. He criticizes cubism for not really giving us a clear account of the external world that exists apart from minds. And he questions their interpretation of the Schrödinger equation and this seemingly arbitrary division they make between observing agents and the systems they observe. Then there's Rön, who raises some concerns about the definitions of key terms in cubism, like what exactly do they mean by agent or world or experience. He argues that they need to be more precise.
It's like they need to tighten up their definitions.
Yeah, exactly.
It's interesting that despite all these criticisms, cubism draws a lot of inspiration from classical American pragmatism, especially William James. How does that connection play out?
Fuchs is very open about this influence. He sees strong parallels between cubism and James's ideas about pure experience and a pluralistic universe where novelty and true randomness are fundamental features.
So it's not all about fixed laws in a predetermined universe.
Not at all. And the cubist emphasis on the now, the present moment of experience, and the active role of the agent, those really resonate with James's rejection of a static block universe where everything is already laid out.
It's a more dynamic and open-ended view.
Exactly. And cubists see similarities with Bohr's thinking as well. Bohr, while not explicitly a pragmatist, was very interested in James's ideas about consciousness and experience.
It's fascinating how these different strands of thought come together. Now, beyond cubism, there are other interpretations of quantum mechanics that also identify as pragmatist.
That's right.
And they share some of those key ideas, like the emphasis on using the theory, rather than seeing it as a perfect representation of reality. So let's explore a few of those. Stapp, for instance, he offers a pragmatist reading of the Copenhagen interpretation.
Yes, Stapp argues that the Copenhagen interpretation, with its focus on the observer and the use of classical language to describe measurement devices, it fits well with James's pragmatism. He sees the goal of science as developing tools and concepts that help us understand and organize our experiences.
Not necessarily building a mirror image of the world as it is.
Exactly. It's about making sense of our human experience, which he sees as being grounded in physical events that we can describe in the language of experiments.
So it's a practical approach to understanding the world.
Very much so.
Then you have Bechtold, who takes a different pragmatist approach, one focused on the practical activities and definitions used in microphysical research.
Yeah, so Bechtold's pragmatism is all about providing practical, workable definitions for terms like preparation and measurement.
Making sure the language we use in physics has a clear connection to what we actually do in experiments.
Right. And he argues that quantum theory, just as it is, does a perfectly good job of providing what we need for successful research in microphysics.
So it's enough to get the job done.
Exactly. And while he acknowledges that his view has some instrumentalist flavor, he distances it from other kinds of instrumentalism by saying that terms like microscopic system do have real meaning. It's just that their meaning is tied to specific sets of experimental procedures.
So it's a very grounded, operational approach.
For sure. Now, Healy's pragmatism is a bit more nuanced. He sees quantum states as objective, but also fundamentally relational.
Objective but relational. How does that work?
So he agrees with QBism that quantum theory isn't giving us a direct picture of some mind-independent reality.
Okay.
But he pushes back hard against QBism's subjectivity. For Healy, quantum states are real, they exist out there, but the way we assign them depends on the relationship between the agent and the system. So different agents can legitimately assign different quantum states to the same system if they have different information.
So it's objective in that the states exist, but the assignment is relative to the observer's knowledge.
Exactly. And he sees quantum theory as offering good advice on how to describe and predict the world given our limited information.
So it's a guide, not a blueprint.
And he argues that this advice is reliable because the Born probabilities, which he also sees as objective, even though they're not degrees of belief or frequencies in his view, these probabilities let us accurately predict the patterns we see in the world. And importantly, unlike QBism, Healy thinks quantum states and probabilities would exist even if there were no agents around to observe them. He also tackles the measurement problem and non-locality, borrowing some strategies from QBism, but doing so within his objective framework.
So he finds ways to address those issues without embracing QBism's radical subjectivity.
Precisely. He emphasizes the role of decoherence in defining when our claims about the world actually have meaning.
That's interesting. It's like decoherence sets the boundaries for what we can meaningfully talk about. Now, we also have Friedrich, who proposes a therapeutic approach rooted in Wittgenstein's philosophy.
Yeah.
How does that fit into this whole pragmatist landscape?
Friedrich's approach focuses on the rules that govern how we assign quantum states. He says the objectivity of those assignments comes from these shared rules, not from some correspondence to an objective reality. Like Healy, he thinks different agents can legitimately assign different states based on their knowledge. And he also uses an epistemic view of quantum states to deal with the measurement problem and non-locality. Decoherence plays a big role for him too. But where he differs from Healy is in how he views meaning and the Born rule. He explores this intriguing idea that claims about quantum magnitudes might all be true in a certain sense, and that the rules governing the Born rule prevent us from running into contradictions when we deal with no-go theorems.
So it's a very nuanced way of thinking about truth and consistency in quantum mechanics.
It really is.
And finally, we have Bruckner and Zeilinger, who see a quantum state as a catalog of an agent's knowledge about a system. Where do they stand in this whole debate?
They're definitely on the side that says a quantum system is fundamentally about information. They say even a simple system can only hold one bit of information, basically a yes or no answer to a question. And they deny that there's some pre-existing objective state out there that we're slowly uncovering through measurement.
It's more about the questions we ask and the answers we get.
Exactly. And Bruckner's recent work, building on Wigner's friend paradox, even suggests that the outcomes we see in measurements might not reflect objective properties of the measurement devices themselves, which pushes their view closer to QBism's agent-centered perspective.
So it's a pretty radical view of quantum measurement.
It is, for sure. So to sum it all up, we've looked at a bunch of philosophical ideas that challenge the traditional realist view of quantum theory. QBism, with its focus on individual beliefs and experiences and these various pragmatist approaches, they all agree that quantum theory isn't a literal picture of some mind-independent reality.
Yeah, right.
It's more about how we use it.
But they differ in how they deal with subjectivity and objectivity. Many pragmatists want to hold on to some form of objectivity, grounded in shared scientific practices and goals, even if they admit that quantum states aren't just mirroring the world as it is.
Exactly. And what's so interesting from a philosophical perspective is that the central question changes.
How so?
Instead of asking, what does quantum theory tell us about the world? These views ask, how can we best use quantum theory to make sense of our experiences? It's a shift in focus.
That's a really insightful way to put it. And it brings us to our final thought for you, our listeners. If we see quantum theory as a user's manual or a source of good advice, how does that change how you think about scientific knowledge and the reality that science is trying to describe?
It's a big question, and QBism and these pragmatist views really force us to think about it.
If you're intrigued, we highly recommend diving into the Stanford Encyclopedia of Philosophy or checking out some of the sources we've mentioned.
This deep dive into these philosophical ideas shows how lively these foundational debates still are, especially for anyone interested in philosophy.
Absolutely. Thanks for joining us on the deep dive. Keep those thought-provoking questions coming. We'll see you next time.